Hello. In the previous section, I discussed the Banach theorems along with some applications. I also talked about weak topology, and we realized that in the finite dimensional case, the weak and strong topologies coincide. For the infinite dimensional case, these two topologies are different. I start with an example here. We consider the unit sphere, as you know, and if the dimensional of E is finite here, is infinite indeed, then we can show that the weak closure of S1 is the unit ball. To show this, we consider a point here in B1, for example. Let 0 in X and assume that the norm of X0 is less than 1. We show that X0 is an element of the weak closure of S1. To prove this, we consider a weak neighborhood of X0, and we know that we may write the weak neighborhoods of any element in the Banach space or norm space by this way. Is the element of E such that the absolute value Fi. For example, I from 1 to n, then we need to show that this neighborhood has an intersection with S1. We need to show this intersection is non-empty. For showing this, we consider there exists some X0 in E with this property. Y0 is non-zero and Fi. Y0 is 0 for I from 1 to n. Why such Y0 exists? And we have not used this assumption yet. Here, we show the existence of this Y0. Assume that such an assume such a y0 doesn't exist. I mean, otherwise, there would be mapping from E to RK. Rn, because we have taken n here, by this definition, we may define x to f1 to fnx, and if we can find such y0, we deduce that by this assumption, the curl of phi is 0, and then phi is the injective and the dimension of E less than the dimension of the range of phi less than n, which is a contradiction. So we can consider this y0, and we use it like this. We define phi. We define a function like this from R to E. E goes to the normal. It's 0 plus y0. Ty0. I want to show that the half line from x0, and assume that this is y0, all this half line is contained in the weak neighborhood X0. If I can show this, then it follows that any weak neighborhood of an element is unbounded in the case that we have an infinite dimensional space. So to show this one, we consider this, and we know that J of x0 J of indeed 0 is the normal x0, and this one less than 1. And we know that the limit of T of t when t goes to infinity is infinity. So by the intermediate, because G is continuous, by the intermediate value theorem, there exists some T0 such that the normal x0 plus x0 y0 is 1. So it follows that 0 plus x0 y0 belongs to S1 because the normals them is 1. And also, if we put x0 plus ty0 here, we know that this point belongs to bx0. And thus, we have established that S or S1, any point of in the unit ball inside the unit ball is a point of the closure, reclosure of S1. So we have B1 as a subset of S1 with weak closure. And we can also prove the reverse inclusion. We have, we can write B1 as the intersection of this weak open set, all the X, such that by the Banach theorems that we add, and this representation for B1 is possible, and you know that these sets are, if we consider this one less than or equal to 1, then this one is weak closed, and the intersection is weak closed. So B1 contains this 1, and it is weakly closed. So we deduce that B1 is S1 weak closure. So from this example, first we deduce that the weak topology is different from the strong topology because we have here S1, which is closed in the strong topology, but the weak topology is the unit ball. And this shows that S1 is not closed with respect to the weak topology. And in this proof, we saw that this half line is contained in Vx0. So Vx0 is a typical neighborhood in the weak topology. So any open set, any non-empty open set in weak topology in the case of infinite dimensional spaces is unbounded. There is a very useful result for the connection between closed sets and weak closed sets when the set is convex. Let C be a convex subset. Then C is closed if and only if it is weak closed. We know that if by the definition of weak topology, every weak closed set is strongly closed always. But for this implication, if C is closed, we need to show that C is weakly closed. We need to show that C complement is open. To do this, we consider some x0, which is not in C, and C complement. And we need to find a weak neighborhood of x0, which is contained in C complement completely. By Banach theorem, from this, we know that if this is C, x0 is in C complement, and so we may separate x0 from C by an affine hyperplane, and because x0 is compact, we may also write some f there exists by the separation or the geometric forms of Banach. There exists some f such that f of x0, and also there exists alpha and a scalar f of x for all x in C. And we define here V as a weak neighborhood of x0. We define like this. All the elements in E such that by using this one, f x minus x0 less than some epsilon. And here, because we have alpha, instead of epsilon, I write alpha. And because we need just f of x0 with less than alpha, I write like this, because here by this inequality, we have in advance that x0 as an element of this V of Vx. So we see that V intersection C is non-empty, because for all elements of C, we have that f of x is greater than, strictly greater than alpha. So we can write this, and from this V, is a subset of C complement, and so it shows that C complement is weak open. So the proof is complete. As a corollary, we may write a part of Mazur theorem let Xn be a sequence in a Banach space which converging to X. Then there exists a sequence Yn made up of convex combinations of Xn converging to this X. there exists Yn like this as a subset of the convex hull of Xn such that Yn converges in norm to X. The proof uses the previous theorem, and it consider a C like this, the convex hull of this sequence. Then C is convex, and if we consider the closure, the strong closure of this set, it is closed. So from this, we deduce that C is weakly closed, and since Xn is a subset of this set, and it is weakly closed, we deduce that X is an element in C. So we can, by this structure, we can find the convex combination of the elements Xn converging to X in the strong topology. There is another corollary of the Banach geometric forms that I like this corollary because I introduced this equality and applied it in several research works. It is interesting for me that A alpha be a family of non-empty, weakly compact, subset of E. And E here can be norm space or a locally convex space, or in general case, this corollary holds, but I mentioned just in norm spaces here. And by this assumption, if A alpha is directed by this inclusion, then the convex closure of the convex hull of this intersection equals to the intersection of the convex hull of A alpha. We see that since these sets are recompact and since they are directed, so this sequence or this family has a finite intersection property, and so by the recompactness, we see that this intersection is non-empty. Obviously, we have this one. So we need to prove this inclusion. Let X be an element of, or A be an element of this intersection, and suppose that A is not an element of the left side. So we need to reach a contradiction. But by these assumptions, we can obtain phi in E star such that and R and epsilon greater than 0 such that phi of A less than R minus epsilon and R plus epsilon less than phi of X for all X in this set. I have used here of the geometric form of the Banach theorem. To get this phi, we have a single point that is compact here, and we find such phi, and then we define HR like this, X in E, with this property, phi of X less than R. We can write R minus epsilon also, but this R is enough. And also we define A star alpha, A alpha intersection HR. And this one is weak close. By the first theorem in this session mentioned, because this one is convex, and by the continuity of phi, we reduce that this one is closed, and A alpha is weakly compact, and then it is weakly closed. So A star is weakly compact. But the point is that we don't know that this set is non-empty. A alpha star is non-empty because if for some beta this set be empty, then it means that for all elements in A beta, we have R less than phi of B. Because when it is empty, it means that we don't have this inequality, so we can write R strictly less than phi of B. And from this, we obtain that for all B in the closure of the convex of A beta we have the same inequality. And we may write here like this. But this A is in this intersection. And so from this, A is an element of A beta. And from this, we deduce that R less than A phi of A, because we have these inequalities here. And this is a contradiction to this one. So A alpha star from here, so we deduce that all the sets A alpha star are non-empty, and they are directed, and they are also weak compact. So we deduce that their intersection is non-empty. The intersection of A alpha star is non-empty, but this intersection is the intersection of A alpha intersection HR. And for any X in this intersection, we have phi of X less than R by the definition of HR here. And this is a contradiction because we had star here, and this contradicts to star. And here I should mention that here we use the closure of convex hull of this set. And I mentioned that this proof works for locally convex spaces. But in locally convex spaces, we know that if E is a locally convex space, we know that the convex, the closed convex hull of a set C, which is even compact, then we cannot deduce that the convex of C, the whole of this is compact. But there is a result due to Krein and Shmulian. The theorem is known as the Krein-Shmulian theorem, as you know, that if E is a Banach space, then for the weak topology, if C is weakly compact, then the closure of the convex hull of C is also weakly compact. But this proof doesn't need that the convex hull of C, when C is compact or A alpha is compact, to be weakly compact. There is also an example that I can mention here. This example is interesting. If we write E equal to L1 and the topology be the coordinate axis vector induced by these elements in L infinity, then we have that E and O is a locally convex space. So here is the topology, the topology on E induced by coordinate wise vectors here. Then taking C be the elements NEN union 0 and L1, C is so compact, but the convex, the closure of the convex hull of C is not so compact. You may check this, and if you need the proof, you may email me. I quickly remind some facts about another topology. It's called weak star topology. If you consider E star the dual of a vector space or non-vector space E, then we have so far two topologies on E star. One is the norm topology, and the second is a weak topology that we denoted by this notation. E star and E double star, because our space here is E star. There is another topology that uses these functions. If you consider this canonical injection from E to E double star, that is defined like this, or I may write f of x for fn E star. Then this n is injective, and the normal n of x is exactly the normal x. So it is continuous and it is linear, but we don't know that n of e is the entire E double star. So if we use the elements of n of e instead of the entire E double star, we obtain a new topology that is called weak star topology. This topology is induced by this element, phi of x from E star to R, and by the notations that we used in the first session of this course. If we use this, and it is exactly n of x, the topology that this family of mappings induce on E star, we obtain a topology that is called weak star topology, and then we may use this notation for this topology. This is a weak star topology. And here the question is that is it Hausdorff? Yes, and the similar properties that we proved for the weak topology hold here, but there are some exceptions. For example, for this topology, we don't have the first theorem proved to date, and we don't have a similar result for that. Generally, I mean that for a convex set, the closure of this convex set is not necessarily in E star. Weak star closed, and but in some cases we may obtain some indeed linear subspaces of E star has such property. And we have now norm weak, and so by this one, weak star topology that is written like this. And the question is that why there is such hysteria over weak topologies, and we try to weaken the topologies. The answer is that a coarser topology has more compact sets, because when you remove some sets from the topology, so the probability that the sets be compact will get higher. So, and there are also some interesting results, like the theorem by Banach al-Oghlu, I mentioned here. Which says that B star, B E star is weak star compact. It is interesting. So the unit ball in the dual of the space is always weak star compact. And you know the value of such compact set because the existence results in minimization, and the importance of this weak star compact sets is known for the people who working on optimization. So I eliminate the proof of this one because it doesn't use Banach geometric forms. And for the second question, the difference between the weak and weak star topology, I mentioned a proposition here, which is interesting. Let phi be a mapping from E star to R. This is a linear functional, and I write it in E star. And assume that, in addition, that phi is weak star continuous. This is a stronger assumption because if phi is continuous from the norm topology of E star to R, we cannot deduce that it is weak star continuous because we don't know first in this stage the topologies are the same or not. But by this proposition, we deduce that for this case, we may find X in E such that phi is exactly n of X. So phi will be in the range of n of E, the canonical injection. So all the linear functionals that are weak continues as this form. I write the proof because it has interesting idea, and it uses the Banach geometric form, and we need this in what follows. Proof of this proposition. The proof lies on non-result in algebra, linear algebra. So we first prove this result. If we have phi 1 until phi k linear functionals from X to R. X is a space, and it's vector space. So we don't need any norm, or it is generally called that if the intersection of the parallel phi I I from 1 to A is a subset of the tail of phi. Then from this one, we deduce phi is a combination, linear combination of this phi I from 1 to k. And these coefficients are in the real line. This lemma is interesting because the proof in linear algebra is different from here. So here we may prove it by using the Banach geometry form indeed. So we consider f from x to rk plus 1 and define like this phi u, phi 1u to the phi ku. And by this assumption, we deduce that phi if we write A as 1, 0, 0, and all of this is 0, then it is not in the range of F from this assumption. It is not, because if all of them are 0, then it must be 0. So this one is not in the range of F here. Now we can use the Banach if A is here and this one is RF. We may separate them by an affine hyperplane like this. And you know that for finite dimensional spaces, the linear functionals have this form. So there exists by Banach theorem F. I can write this F by this way. And there exists also alpha such that we have f of A f of A here is exactly here. The first one is multiplied by lambda, and we have this one and this one less than alpha, and alpha less than f of I can write u for all un r f, and the right side is exactly lambda pi, because the first one is multiplied by the first one, and we have for the others, and we can write this sigma lambda I pi I u, the other from 1 to k. And because here we have this one for all u, because here we have u, this one is indeed f of u, and u is an element, arbitrary element in X, and so since it is a vector space by factorization of coefficients and tending to infinity, we deduce that this right side is 0. And from this, we deduce that phi is a linear combination of this functions phi I, but the coefficient here is non-zero because if this one is 0 and these inequalities are strict, so this coefficient is non-zero, and so phi is a linear combination of the functions phi I. I use this lemma to prove the theorem that we have, or the proposition that I wrote here. So I continue to the proof here. Since phi is continuous here for the weak star topology, so we may consider a neighborhood of 0 in for the weak star topology. This neighborhood of 0 to the next for the next weak star topology with this property. There exists B0 such that phi of f less than 1 for all affinities. We have used the continuity of phi in the point 0, and this is the definition of the normal definition of the continuity here. So we use this. We know that the structure of neighborhoods is like this. We may write V of 0 in this way, in E star, that the absolute value, because it's a neighborhood of 0, and it's possible to write like this. And then in the particular case, we know that n of xi, if we write like this, is 0 by the above. So we consider this for the f's that for the elements f that has this property. So I write, if we have this one, then deduce n of xi of kf for all k in natural numbers. We also have this one by the linearity. And from this one, I deduce that phi of kf less than 1 for all k. Why we can write this? We had a lemma before this one that if the kernels of a finite number of linear mappings is 0, and then we deduce that phi is 0, then phi is a linear combination of that mapping. So I write here if we have this one. If we have this one, using this, we have this one. And then we obtain this one. Because for this elements, the elements in V0, we have this inequality. And from this one, by tending k to 0 and writing k in denominator of 1, like 5k, less than 1 over k, we deduce that phi is 0. Phi of f. So we have from I to k, from this we deduce that phi of fi is 0 for all I. For f, not. So by the lemma, we arrive at this. Phi is a linear combination of phi or n xi. And by writing this as an n of sigma lambda I xi, and writing this as x0, we deduce that phi is indeed n of x0. And the proof is complete. So there is an application of this proposition to show that the convex hull of a weak star compact set is not indeed a closed set is not necessarily weak star closed. I write it here. So first, I mentioned that when C is weak star closed, we cannot deduce that this one is weak star closed by this corollary of this proposition. Assume that H is a hyperplane in E star and be defined by this one. If in E star such that this hyperplane and we want to obtain this, but first we have assume that we have this one, and also assume that it is let H is weak star closed. So we deduce that there exists x0 in E such that x0 is non-zero, and H is the set F in E star such that instead of phi, we may write n of x0 and f. It means that the closed weak star closed sets which are hyperplane have this form. We can find some n of x0 that we can write instead of phi. And if we have this one, we know that n from E to E level star is not on 2. And necessarily we have that. We don't have that. This one is EX star. And the spaces that this equality holds are called reflexive. And there are some examples that we will see of non-reflexive spaces. So this canonical injection is not on 2 necessarily. So this shows that the hyperplanes are not necessarily weak star closed, because we can find some phi which is not in N of E. First, we prove this corollary. Let F0 be an element of H complement. By our assumption, this H is weak star closed. So this one is weak star open. So we can find the weak star neighborhood of F0 like this. We define this. F minus F0 and xi less than epsilon I from 1, okay? And we may consider this neighborhood in the way that it is a subset of H complement, because H complement is open. And we know that this intersection H is the empty set, because B is in the complement of H. From this, and from the fact that B is convex, we see that phi of F less than alpha for all F in B. Either we have this one, or we have this for all F in B. Because the structure of V is a convex. Convex here, V is F means V F0. it is convex, and H has this structure equals alpha. If for some elements of V, we have less than, it means some part of it is in a half-ended space, and the other part is in another half space. Since V is convex, so we may find an element that is exactly alpha, and it is impossible because the intersection is non-empty. So we may write these two assertions, either first or the second. We consider this one. We assume that we have this. And we define W here be the set V minus F0. For any elements of this W, we have this inequality. Phi of G less than alpha minus phi of F0, because for the elements of V, we always have phi of alpha, phi of F less than alpha. So we have used this one. And also we have that W is equal to minus W. And for proving this, we can apply the result here and the structure of V. I write the proof here. For this one, we consider G in minus W, which is minus V plus F0. And then we may write G as minus F plus F0. And we may write minus F plus 2 F0 minus F0. If we show this one is NV, we have obtained the equality. But this is easy because we have minus F plus 2 F0 minus F0 xi. And if we write this one as minus F plus F0, from the definition of Vf0, we have that this absolute value is less than epsilon. So we have that this one, this term is an element of V and minus F0, and it's an element of W, because the structure of W is V minus F0. So by using this one, we obtain the absolute value of phi of G less than alpha minus F0. Here we know that W. Since V is a weak star neighborhood, we deduce that W is weak star open, and so W is weak star open, and from this we deduce, because it's a constant, it is linear, and we have for an open in the weak star topology this inequality. So we deduce that phi is weak star continuous. And by the proposition, we deduce that the existence of some x0, such that phi is n of x0. And this is what we wanted to show, the existence of this one. We also learned from this result that convex sets that are closed in the strong topology need not be closed in the weak star topology. So, as I explained before. But reflexive spaces are the spaces that in the canonical injection from E to E star, if this one is surjective, then we say that E is reflexive. And there are many examples of reflexive spaces. In fact, for example, finite dimensional spaces. Because N is injective, and if the dimension is finite, then it is on 2, and so these spaces are reflexive. Also, it is known that LP spaces, or P, between 1 and infinity are reflexive, and also Hilbert spaces, and but L1, L infinity by capital L, and CK when K is compact, and so many other spaces are shown that they are not reflexive. We have a result about reflexive spaces that is interesting. This theorem that is mentioned in several books as Kakutani result. I just mentioned here is reflexive if and only if the unit ball of E is weak compact. For the Banach theorem, we saw that always in the weak star topology, the unit ball is weak star compact, but here B is weak star compact if and only if E is reflexive. I write some outline of the proof. We know that if we have the reflexivity, then we know that NPE is exactly PE double star. And since it is one-to-one and isometric and the other properties that we saw, we may write N inverse from PE double star to PE, which is by the definition of N, this one is weak star to weak continuous. So by the Banach algorithm, we see that N inverse of B double star, which is weak star compact, is weak compact. So the corollary of the Banach algorithm theorem. And the converse, for the reverse, I write here, I mention a result. It's known as Goldstein, that says for any Banach space, this N has this property, N of if closure with respect to the weak star topology is dense in E double star. We can use this one for the unit ball here and obtain the reverse. There is another result that was to be mentioned here, a Berlin Shumulia. A Berlin Shumulian that says if C is weakly compact, and it is equivalent to say that every sequence Xn in C admits a weakly convergent subsequence. There exists Xni converges to some Y with the weak topology. And this is a nice theorem because we don't have a meter on the weak topology, but usually we have such results for the metric spaces. And moreover, for the weak star topology, we don't have such result. For the weak star topology, For example, if we consider En be this sequence, E1 be 0, 0, E2, the base, for example, time. This place. If we consider En like this as elements of L1, and we know that L1 is a subset of L infinity star. And we consider some F as -1 to the K1, -1 to the K2, and -1 to the Kn, so on. We see that F of En is -1 to this power, and by this one, we deduce that there is no subsequence of Xn converging in the weak star topology. This is an interesting example. Yes. There is another category of Banach spaces called uniformly convex space. First, I recall the definition of strictly convex spaces or Banach spaces. If you consider the unit ball, and if for any two elements like X and Y on the sphere, this line, the line segment that connects X and Y, be inside the unit bar. And in this case, we say that the space is strictly convex. If the unit bar has this form, for example, and this line segment completely lies outside the inner of the unit ball. So this one is not strictly convex. Not, but this one is strictly convex, and it is smooth. The sphere is smooth, and for these cases, that the sphere is enough. Roten, we say that it is strictly convex. We had such examples. For this one, the norm is the Euclidean norm, and for this one, we may write the maximum norm. And also, you may have other examples. This one is like in infinity, L infinity, but the finite dimensional. And we had this one also. And we mentioned this as a rhombus, that the norm is like L1. But there is a uniform definition for strictly convexity that is called uniformly convex. Uniformly convexity. Here, I first mentioned the definition for all epsilon greater than 0, there exists delta such that for all x and y in via E, if the normal x minus y greater than epsilon, it means that they are at least as far as apart as epsilon, then we deduce that this one is less than 1 minus delta, and we see that this is a uniform, an uniform definition of strict convexity. It says that if this is the unit ball and x and y here have a distance greater than epsilon at least, then the middle point here lies on a ball with a radius 1 minus delta, and it means that there is a here distance from the inner sphere from the outer one, at least it is delta when we choose x and y far from them. And this is the examples. You see that this one and this one with these norms. This norm is indeed x and y is defined by, I call it norm 1, the absolute value of x and y. And this one, we may call it norm infinity by this definition, the absolute value of this, the maximum of them. And here we have the examples in R2, and we see that this one is the dual space of the norm 1. It's easy to check. And so these two examples are not also uniformly convex, but this one is rotund enough and it is uniformly convex. But there are some classic examples also to mention that they are uniformly convex. For example, you see that H, the Hilbert space, is uniformly convex, and LP between LP spaces, for example, L2 by capital L and L, they are uniformly convex, and we may also define a modulus here, a modulus of uniform convexity that is defined by this from 0 and 2, because we choose our points in the unit ball, and the distance between 2 points can be 0 and 2, and we define this theta be like this for any epsilon greater than 1 if, and x and y in DE if the norm of x minus y be greater than equal to epsilon, then we have for the middle point of x and y, this inequality less than 1 minus eta epsilon. And this eta epsilon is exactly the delta here. We may define this one because for uniformly convex Banach spaces, the existence of this delta is in the premises. There is a theorem which is important, Millman-Pettis. It says that a uniformly convex Banach space is reflexive. And why it is so important? Because the uniform convexity is a geometric property. We define these inequalities on the norm, and it is related to the geometry of these Banach spaces. So, geometric property. And for the reflexivity, we use the canonical injection, and we say that it is onto, and we have here a topological property, because we know that N of E with the weak star topology, the closure is, or NE is dense in EW star, and this property we always have this one, and by the reflexivity it means that this one indeed equals to N of E. So from a geometric property, we deduce the topological property by the Millman-Pettis theorem. The proof is interesting. It has some ideas that worth to be mentioned here. For the reflexivity, we need to show that N of E equals E double star. To prove this, it's enough to show that N of VE equals to N of BE double star. So we prove this one, and to show this one, we consider some zeta in N of BE. To show, no, this is not correct. N of BE is B E double star. We need to show this one. We know that N of BE is a subset of BE double star. So we consider this one is abused. We consider an element in B E double star, and we find, so I write here zeta in B E double star, and we look for some element in BE with this property. For all, I write like this. There exists some X in BE such that the norm of zeta minus N of X less than epsilon. If we prove this one, we have proved that zeta is exactly N of X because epsilon here is arbitrary, and we have obtained the result generally. So for all, so it is better to, because it doesn't implies the equation here, it is important to write this as this. There exists, I need to show that there exists X such that for all epsilon greater than 0, we have this one. It is important that this one is correct. So we consider an epsilon first, and then we find X that is which doesn't depend on that epsilon, and let delta be eta of epsilon, and assume that this is the modulus of a modulus of convex uniform convexity. So, and for this delta, we can choose some F in E star such that the norm of F B1 and the zeta position with F greater than 1 minus delta 2. It is possible because here we have the norm of zeta equals to 1, and by the definition of the norm, we can find this one because the norm is the supremum of zeta over all the elements in the, can be in the unit sphere or the bond. And we define B like this, tau in E double star such that the absolute value of tau minus zeta, and if less than this fraction, delta over 2. We define this. And this is a neighborhood of zeta here. And since tau here is taken from E star, and if here is taken in E star, it is a weakest star neighborhood of zeta. So it is in neighborhood in the weakest star topology for E double star is denoted by this one usually. And we know that n of B E with the weakest star topology equals to E double star by Goldstein theorem that I mentioned before. And we also know that the intersection of V with n of VE is non-empty since V is a weak star neighborhood of zeta. Indeed, this is a weak star neighborhood of zeta, and the normal zeta is 1. So we have this one. And we deduce that there exists X in VE since it is non-empty with the property that J of X is in V, this way. And we show that X satisfies this property. You know, this is our claim. If we show this for all epsilon